Welcome, everyone. I would like to express that we are very grateful for this interest in the topic, and thank you for taking the time to join us for this webinar session today. My name is Katharina, and I will moderate today's webinar with the subject Modern Cleaners, Shaping the Future of Sustainable Industrial Cleaning. First and foremost, I would like to introduce to you Neil Patton, who is our speaker and subject expert today. Neil holds a degree in chemistry and is a product management and business development professional with more than 30 years of experience. He has extensive knowledge of the supply and support of chemical processes, technology and equipment to the metal finishing and printed circuit board industries. This includes key account management and decades of working with electroplaters, tier suppliers, OEMs, environmental agencies, and industry associations. Neil is the Global Product Manager for Cleaners, Strippers and Pretreatment for MKS Atotech's General Metal Finishing Business Unit. Welcome, Neil. A couple of words about the webinar before we start. The webinar will be divided into two major parts. We have about 50 minutes presentation and 10 minutes Q&A session. I encourage you to raise questions during the presentation, and therefore please use the Q&A function, which you can find in your control panel. Keeping confidentiality, we will not publish the question, so you can only see the question which you have posted yourself into the section. We will try to cover as many questions as possible during the planned Q&A session at the end of the presentation. Of course, if time allows, we will answer all questions right away. Also, Neil will be available after the webinar to reach out to you via email. Last but not least, there will be a recording available after this webinar session, and we will let you know when it is released and send the link via email to you. So now let me hand over to Neil, and please enjoy the session.
So thank you very much, Katharina, and welcome everybody. Yes, we're excited today to discuss with you our sort of cleaning and modernizing cleaners. And the main aim of today's webinar is to give you a general overview of cleaners, especially soak cleaners for metal substrates, and basically what has gone before, what can be improved, to show you some of the benefits of these improvements, and then to give you an idea of some of the newer products or a new process that's been developed to show you the benefits of modernizing even such a generic process as soak cleaning. So as you can see from the agenda, there's quite a lot to get through. The first half is mainly relating to soak cleaners, cleaning in general, and how you benchmark. And then the latter half is more to do with the latest development and some of the benchmarking results and how to control the bath, etc. So I will continue with the introduction. So as we know, for aqueous cleaners, there are several main types, especially when we're talking about immersion cleaners. This will be the focus of today's webinar. We have emulsifying or de-emulsifying type cleaners. De-emulsifying can also be referred to as rejecting or displacement type cleaning. We have electrolytic cleaners, so electro cleaners, spray cleaners, of course, and you can also have soak cleaners where you also have ultrasonic support for even better cleaning performance. And of course, not only do we have these types of cleaners, you can also have acidic cleaners, as well as these primarily alkaline immersion cleaners, etc. Not only do we have these different styles of cleaners, we also have different ways of preparing them ready for doing makeups. Quite a popular version is a type of solid or powder all-in-one type cleaner. This is where all of the components are mixed in a powder form. And so it's considered to be one of the most economical, as everything is highly concentrated. We have liquid all-in-ones where you obviously have water and you mix everything together in water. This also has its benefits, we'll discuss later on. And there's even a mixture where you can actually have a type of additive package where sodium hydroxide, which is typically found in metal cleaners, these alkaline aqueous cleaners. Sodium hydroxide or potassium hydroxide can be added on its own, and then an additive package is added on top to give you the cleaning, the surfactants, and the other components. Now, if we look at solid versus liquid cleaners, the reason I'm showing this is quite important for the development of our new processes and modernizing our cleaner portfolio. Solid powders all-in-ones are quite well known. They are quite dusty, although they're relatively cheap. As you can see as a benefit here, you can see also that they're relatively dusty because of the way that they're manufactured. You can only add these manually. You literally have to shovel these in and mix them up. You can get issues with caking. If you're in a high humidity area, for example, or region, moisture can be absorbed into the powder, and then you get this sort of huge tablet formed. The dissolution can take time. Sometimes you need a lot of time to dissolve it and get it to slowly dissolve in. And again, getting some form of homogeneity of the powders and all of the other additives, mixing them up, trying to get them to mix beautifully is not so easy. So you can sometimes find at the top of a bag, it's slightly different to at the bottom of a bag. And again, because this is a dry mix, if you want to add some liquid surfactants or liquid additives, which only come in liquid form, of course, you're limited to how much you can add without running into this issue of caking. Liquids, again, they have quite a few benefits. Basically, they're easy to make up. Of course, you have no dusts. You can use dosing pumps, etc. When you're adding it, they're not so concentrated, so they mix easier, so you don't get this type of boil over where you have sort of high concentrations of sodium hydroxide, say, in one place, like you would with a solid. And again, there's no caking as it's not a solid mix. However, there is the slight issue is that, of course, it contains a lot of water, which means you have less of the active ingredients, which means that you can have per kilo a higher makeup or operating cost. And also, again, we have this issue of mixing different components together, especially organics and inorganics, where you can form a type of oil out or incompatibility. So again, both solids and liquids have their benefits. The liquids is the easiest to use, but has some issues with costings and with solution formulas. And the additive packages here, again, someone takes sodium hydroxide and adds it themselves. And then you have an additive package where you have a lot of builders, additives, surfactants all mixed together. Again, this runs into the same issue as with liquid cleaners. You have not so much flexibility in the formulation due to the mixing such different styles of components. And again, there you also can't have it so concentrated because of this mixing. And that has an influence on the eventual operating costs. So now you've seen the styles of cleaners. If we have a look at a typical soap cleaner composition, a soap cleaner is made up of mainly three different sets of components. We have what we call builders. So these have been mentioned before, the hydroxide, sodium hydroxide, potassium hydroxide, various carbonates, bicarbonates, etc. Again, giving you some form of alkalinity. Silicates, they have various functionalities. Even things like phosphates and borates, we'll mention these a little later on. These also have some functionality, but are not so desirable. Surfactants, again, we have the generic types, the non-ionics, the anionics, amphoterics, and cationics. You typically would find the non-ionics and anionics in such soap cleaners, and rarely would you see an amphoteric or cationic, but they're sometimes present. And for additives, again, you have a lot of different additives for different functionalities, chelators to try to mop up either hard water or metals that get dissolved in the solution, reducing agents, typically if you've got something like Chrom 6 around, various solvents, this can help with cleaning, but also with helping dissolve surfactants. etc., and things like dispersants, which are types of surfactants, and then things like nitrates, amines, nitrites, sulfates, and chlorides, which again have various functionalities for certain applications. Now, one thing that's quite well known is that if you were to just take a solution of sodium hydroxide, for example, and try to clean some parts, you would get limited results. If you were to get just a solution of water and some surfactants, you would also get limited cleaning effect. But when you add a builder together with a surfactant package, of course they have to be compatible, then you actually get a extremely, you get a synergistic effect from both of them, and you can boost the cleaning performance significantly by having the right mixture of a builder and surfactant packages. So that use the right builders and surfactant mixtures, you can have a very good cleaning effect. Now, when we're making a soap cleaner, there are various things we need to take into account. One of those, again, is the types of chemicals that are used. This is critical. As everyone knows, there are lots of things like REACH, lots of legislations out there regarding different chemicals, different raw materials, and again, these are also relevant for cleaners. And one of the things we try to do when we're formulating such cleaners is to avoid the use of harmful chemicals. Not only is this bad for employees, operators that are using them or handling them, but of course you can have a direct effect on the environment, and also there are quite a lot of restrictions nowadays on what you can discharge from a facility, and of course then wastewater treatment, the simpler it is, the cheaper it is, the better. So again, the choice of chemicals, not only that, but also the concentrations. If you have highly concentrated chemicals, and even if you have, shall we say, low makeup or low lifetimes of baths, of course, this means that your discharge of chemicals or concentrated chemicals is higher. And this means that, of course, you can get increased pollution. So again, reducing the concentrations of chemicals is also a way of improving the situation. And again, what is becoming very apparent lately is the CO2 footprint of a process. And with soap cleaners, they have typically been used at higher temperatures for improved cleaning effect. And again, this means that you need to input a lot more energy to keep the bath temperature up. And this, of course, negatively affects your CO2 footprint. As you can imagine, one of the main aims of MKS Atotech is to reduce the environmental impact of our processes as much as possible. And for the development and modernizing of cleaners, this is no exception. When we are talking about removing substances of, should we say, concern, of course, CMR, so carcinogenic substances should be avoided at all costs for obvious reasons. This is definitely for the protection of workers. Recently, there's been a lot of work on the banning of APEs, which are alkyl phenol ethoxylates. Typically, these are NPEs, non-alphenol ethoxylates, and even octyl phenol ethoxylates, the 8-chain surfactants. These have various problems. Biodegradability, you'll see that all of these are relatively legislated against. Surfactants, for example, in Europe, in the EU, they have to have a certain biodegradability, so they have to degrade by something like 80% within a certain fixed period of time. APEs have been banned for more than 10 years now. And there are also additives that are used like amines. They can help with cleaning, they can help with giving you some alkalinity. The only problem with them is, of course, they're a source of nitrogen, and as well, they are a hard complexer, which makes wastewater treatment more difficult. And talking about hard complexes, EDTA and analogs of this type of complex are also quite commonly used. And again, this makes the wastewater treatment of such a cleaner pretty difficult, and also means that you typically have to put it into a separate waste stream, a complexing waste stream, to be dealt with a more complicated wastewater treatment process. There are things like boron compounds, typically used for sort of nearer neutral cleaners for some of the softer substrates. But again, borates, borons are considered hazardous and avoided where possible. Phosphor and nitrates, nitrites, these can also be very useful for various functionalities. However, they also can get into water courses where you get eutrophication, which basically means, should we say, overfeeding or making the waters too rich for algae and things like this. You get algal blooms, which of course are deadly for fish and aquatic animals. So again, if we can avoid all of these common substances when we're formulating cleaners, then all the better. What some people fail to think about, again, is of course that raw materials, just like everything, they also have limited lifetime, shall we say. Not only can some of the older raw materials, especially things like surfactants that are used in soap cleaners, not only do these have issues, legislative, think of the APEs, these were quite common in soap cleaners. However, of course, issues were found with them over time, and now they've been banned. So again, when looking at formulating soap cleaners, we should look into what raw materials are available, which ones look like they are more, should we say, generic, more accepted, used in a lot of industries, and look as if they have a longer future. Again, if you are using older raw materials, you can have single sources, so just one supplier. And we have even seen some suppliers actually only have one reaction vessel for creating some of their organics. So you can imagine if that vessel broke down or there was an accident, then there is no supply at all, meaning a very, very quick risk of stop of supply, which means then trying to produce cleaners from this would be very difficult and would mean quite extreme actions required to replace the product. And also quite often you'll find that there are no local equivalents, so you have to import a lot of these more exotic, older products or raw materials, and again, this adds to more cost, etc. So again, when thinking about reformulating, we should consider the raw materials, especially along the surfactant side. We mentioned high temperature operation. This is mainly because if anybody knows anything about cleaning, what we tend to know is that if you're struggling with cleaning or you want to improve your cleaning capability, you typically have various ways of improving this. One is to increase your chemistry, so increase the concentration of the cleaner you're using. This can help to improve cleaning. You can use agitation. If you were to do this at home, you would use some form of scrubbing, for example. This would help to remove any contamination from the surface of whatever you're cleaning. And in a typical bath, this would mean either solution movement or rack movement, for example. Time, another thing is you just soak, leave it in there for 10, 20 minutes, leave it there for a lot longer. This helps to improve cleaning typically, or you increase temperature. Now, in an industrial application where you have a lot of parts being processed, time is of the essence, so you don't always have 10, 15 minutes to get the optimum cleaning. So typically time is limited. Agitation, you don't see that much solution movement and definitely not parts movement for quite a lot of applications. So again, this can be quite limited. And again, the chemistry is what it is. These are typically chosen to be sort of cheaper chemicals so that the process costs are not so extreme. And that therefore means that the only thing that you can change is the temperature, which means you just tweak up the temperature to take into account the fact that you have maybe less efficient chemistry, no agitation, and a limited amount of time, which is why you typically find that soak cleaners have high operating temperatures. There are other reasons on top. There are certain contaminations that only can be cleaned at high temperatures, sort of waxy deposits, for example. But again, for the majority of oily type contamination we see for metal parts, you can get away with lower temperatures if you adjust some of these other parameters. So if we wanted to reduce the temperature, again, why would we be doing this? Again, as you can imagine at the moment, there's a lot of talk about reducing the temperature, having cold cleaners, especially in the metal finishing market. Again, this is mainly to reduce cost, but also to meet CO2 footprint demands. And this is by reducing the energy you require for heating. There have been some lower temperature cleaners. However, sometimes you do see some compromise on cleaning efficiency. You maybe have to increase the immersion time or replace the bath more often, or you actually have to increase the concentration a lot to give you the same cleaning effect as you would have had at, say, 60 degrees. However, we do know that in most processes, you cannot compromise at all on cleaning performance. The parts have to come out without any defects. So you can get lowered operating temperatures, but again, you have to make sure that you have the same or better cleaning efficiency. You don't adjust the time too much. You get a reasonable bath lifetime to make sure you don't have the same waste and costs involved. And again, to ensure that you don't increase your rejects. So if we want to compare a normal, should we say, higher temperature soak cleaner versus a low temperature soak cleaner. Here, basically what I've done is we have an Excel table that takes into account a soak cleaner bath sitting there. Soak cleaner bath sitting there in this case in a plastic tank, obviously with an open top with a little bit of extraction. We have assumed that there are 2 tons of steel going through this cleaner every hour. Again, these steel parts will be at room temperature. And what we have done is we have compared a bath running at 65 degrees centigrade, which is a good average for a hot soak cleaner, versus a soak cleaner that could be run at 35 degrees centigrade. And we've taken some rough values for the CO2 per kilowatt hour and the costing per kilowatt hour from the European Union. And as you can see here, that you can imagine that the heating costs or the energy required for heating of a 65 degrees centigrade bath is a lot higher than a 35 degrees centigrade bath. And of course, the parts that come in, putting 2 tons of cold parts into a bath will mean the bath cools down, which then you have to compensate for. So again, you can imagine that at 65 degrees centigrade, you have to put a lot more energy in. And the upshot is that with all of this, you would find that within 1 year, you would save about 85,000 kilowatt hours of energy. This equates to about 19,000 euros, which is quite a good saving just on electricity. If you consider that a soak cleaning process is not that expensive to run. And again, you can also reduce your CO2 output by over 22 tons. So again, this is a definite benefit for going for a cooler soak cleaner. So again, the idea of going cold is very, very, very attractive. Bath lifetime. This again, as we said, influences pricing. This the process cost of a soak cleaner. This also influences the amount of waste that you generate. And to have an increased bath lifetime, it helps if the cleaner has a naturally good high cleaning performance, so that when it is used, slowly but surely it'll become contaminated, but it can handle this a lot more. So you have a good performance anyway at the beginning, which degrades over time. You then have a oil contamination capacity, especially for emulsifying type cleaners, how much oil can the cleaner take before the cleaning performance degrades so much that you have to replace it. And also, if you have methods to reduce the amount of contamination in the bath, if you can implement these, this then also increases the lifetime of the soap cleaner, giving you better costings and, of course, less makeups and waste. A big influence from formulations, again, is partially from the builders, but mainly from the surfactant mixtures that are used and additives. This is one good way to influence oil capacity and cleaning performance. So if you can generate a new formulation that has excellent cleaning and oil capacity, you can increase the lifetime of a soap cleaner. So if we're talking about process costs, a soap cleaner is not one of the most expensive processes on a, say, electroplating line or a painting line, for example, but it still has to be within a certain economic range. Again, what considerations are there for process costs? Typically, you can get high cleaner process costs if the cleaner itself per kilo, for example, or liter is high, of course. The makeup concentration, it doesn't make any difference if it's half the price per kilo if you have to make it up at 4 times the concentration. So again, this has an influence on the operating cost. The dosing amount, how much do you need to replenish for each square meter, ton of parts that have gone through? The lifetime, do you have to change it every week or can you change it every 2 months? Operator costs, if you've got lots of makeups or you need to do a lot of maintenance, you have a lot more costs for operators. Treatment costs, again, this is the waste treatment. If it's easy to treat, this is lower. If you have a lot of chelators, for example, it can be higher. Waste costs, again, how much is generated and how much does it cost to actually get rid of filter cake, for example. And again, parts reject rate. If the cleaner's not performing well, this can cost you a lot more. This is an indirect cost that you can associate with poor cleaning. And again, energy consumption. So again, if we can address most of these, then we can also create a modern cleaner portfolio that is also more cost effective. So now you've got an idea of the types of cleaners, the sort of groups that we see them, and some of the main factors that influence cleaners and what we would look at if we were developing new cleaners. And again, if you're going to do this, how do you actually test the efficiency of soap cleaners and various capabilities? There are a lot of different tests possible, but the main criteria would be things like cleaning efficiency, oil capacity, foaming and defoaming, and substrate attack. So cleaning efficiency is obvious, and oil capacity we've discussed. Foaming and defoaming, this can have an influence for just the practicalities. If you have a highly surfactant-based cleaner and it foams out of the tank, this of course then means you have an alkali foam going all over the floor, which can of course cause issues. So lower foaming is better. Substrate attack, again, cleaners are typically grouped into what substrates they are compatible with. There are a lot of cleaners for steels, for example. Then if you want to go down to the more softer or more susceptible substrates like copper alloys, zinc alloys, and even aluminium alloys, you then also have specialist cleaners that don't attack these substrates so that your parts aren't damaged while you're trying to clean them. So again, these are critical for development on testing of new cleaners. If you want to test cleaning efficiency, as we discussed before, again, appearance, you can actually look at a part and say, is the thing clean? There's things like water break tests. I think these are classic tests where you see if you get a de-wetting of a surface after you've cleaned it, which is indicative that it's not been cleaned. Gravimetric testing, you have contamination, you remove contamination, you can measure the weight difference. There are things like the Atotech cleanliness tester, and this is Another method for looking at organic contamination on the surface using a piece of equipment. Copper immersion. Again, you use a copper sulfate solution, especially for steel substrates, and you immerse the part, and if the part is evenly covered in a nice copper layer, then you see that it's been cleaned properly. And then there's Dynix, and this looks at the surface tension of a part, and you can tell by the surface tension whether or not it's been cleaned enough. So we can look at, so those are typical cleaning tests, and yes, all of these were used for our evaluations and benchmarking. Oil selection. If you're going to do testing, you cannot just take one part from one industry and say, right, we'll use this as our benchmark part and go from there. What you also need to do is take into account that the metal finishing industry is very wide and varied, meaning that there are a lot of different oils, coolants, rust prevention, and various other additives and things that are used when machining and processing parts, stamping them, drilling them, cutting threads, etc. So what we did was we looked at the industry as a whole. We looked at a lot of different oils being used and different coolants, and chose quite a few of them, and then put these into different families, and then tested which oils we could take as a good representative of those different families. So basically what you do is, what we did is we highlighted something like from dozens of different oils, we highlighted about 7 or 8 and managed to come down to a few oils that we tested. And we also prepared certain parts. As you can see here, we've got various parts with bends in them, etc., just standard plates. And we've added different oils to them, baked them on to make it even more difficult. And what we try to do is also make these parts overly contaminated so that you have something to measure. So as an example, here you have a contaminated part. And again, after it's been cleaned, and here you can see whether there's any residues, especially in the corners, etc., and use this as a type of guide as to whether or not the cleaner is performing well or not. So that's a visual evaluation. We also have the water break test. As you can see here, this is a standard wholesale panel which has been cleaned, but it looks like here in the corner there's still some organic remains, which means that the water cannot wet it properly. So you can see that in this corner there is a water break, therefore this is not fully cleaned. Again, this is more of a visual inspection. Gravimetric, I think by its by its general name, we know that you basically take a part, contaminate it, and measure the weight before and after cleaning to see how much of the contamination has been removed. In this case, we artificially contaminated parts. We baked them at 180 degrees for 3 hours to make sure that the oil or whatever was baked on there, really difficult to remove. And then we did our various benchmarking of different cleaners and formulations. And from this, you get a value of weight loss of contamination. Of course, the higher the weight loss, the better the result. The copper immersion test, like we said before, you take copper sulfate, you add a steel part into it, and if you get a nice uniform thick coat like here on the right, this is indicative of good cleaning, and on the left here of marginal cleaning. So you get some copper deposition, but you can see areas where it's not so well deposited. This shows you that the part is cleaned, but not very well cleaned. So there's still some residue. Dynix, again, this is just measuring the surface tension. The higher the surface tension, the better. This indicates that you have a cleaner surface. The lower the surface tension, the worse. And as you can see here, between 50 and 60, so 60 is a failure, 50 is a pass. So somewhere between 50 and 60 is probably the surface tension of this part. And depending on the parts, depending on the cleaning, depending on the setup, this may or may not be still acceptable for cleanliness of for a certain plater, for example, doing zinc plating on steel parts. So again, where the failure is or where the surface tension is always determined by the application and cleaning requirements. There is, again, as we discussed, this Attutech cleanliness tester. Basically, this uses ultraviolet light. You have a controller, you have a transmitter. This transmits ultraviolet light onto the substrate. This then initiates, basically interacts with any organic contamination on the surface. This then absorbs the ultraviolet light and typically re-emits light at a different frequency. And the more light that is re-emitted, the higher the amount of, or the higher the contamination of organics on the surface. So a high number is indicative of higher contamination, a lower number of cleanliness, should we say. So 98.7% would be a very clean surface, for example. And just so you can see what the unit would look like, again, you have the transmitter emitter here, there's a controller, and there's your test piece here. So relatively simple, and you can use this again to set a number for specific parts. If you have a process, you can take some parts, run them through, and then see near the end of a week or near the end of when you think the soap cleaner might be getting tired, you can then start checking parts and seeing if the cleanliness is still good enough or not. So this is also a good tool for measuring cleanliness. Oil capacity test. Again, this is a relatively simple test. You take a solution of the bath, you add a fixed amount of oil, you shake this up, and then basically try to find out how much of that oil has been emulsified. So in this case, it's for an emulsifying cleaner, and how much hasn't been. And the remaining oil on the surface will be basically oil that has not been emulsified. And therefore you can work out a percentage oil capacity. So how much oil per liter can a certain cleaner take up. And different oils have different oils and different cleaners have different abilities with different so different oils, and so a cleaner can have different capabilities with one oil. So very good with one type of oil, but maybe a poor oil capacity with a different type of oil. This can be quite common. So it's also very useful for formulating more universal cleaners that are better with a better range of oils, or a wider range of oils. Foaming, defoaming, again, this is, there are several methods of doing this. There's a shake method. In this case, this is you take a fixed amount of solution, you bubble for a fixed amount of time until you get a maximum amount of foaming. So here you've got basically an air pump and effectively an air brick or a bubbler you would use in an aquarium. And you bubble this in the liquid. This then generates some foaming. You then get a certain height of foam or maximum foaming, and then you switch off the pump and let the solution defoam, and you just measure how long it takes to reach maximum foam and how long it takes to then defoam back down to the original liquid itself. And by measuring this, you can look at the foaming and defoaming characteristics of a cleaner. And of course, the better would be that it takes a long time to foam and then defoams very quickly. This would be ideal. And of course, the maximum foaming should be as low as possible as well. So those are different ways of testing, which we use during our processes. From now that we know what the cleaners are like, now we know what we're trying to aim for. So, you know, costings, efficiency, capability, temperatures. We also started looking at different concepts. So for how would you modify the modernized cleaners? So the motivation, of course, is to try to keep liquid products, especially the easy handling, etc., safety for users, and of course, formulation flexibility. We also wanted to reduce the effects of raw material incompatibility. As we said, if you have solids, you have issues adding liquids. If you have liquids, adding certain surfactants to certain builders is not ideal. So this we wanted to take into account, and of course, to look at the concentrations of such liquid products to try to minimize their costings and to improve reduce processing costs with such products. So again, to do this, we decided to come up with 2K concepts, so two-component concept where you have a separate builders and surfactant products. And again, so we now have liquid products where we want to have two products to make up one process. So this is what we want. And again, we are aiming for more environmentally friendly, sustainable, technically superior, cost effective. And of course, because we have two different packages, a builder and a surfactant package, we also wanted to build up a portfolio of different packages where we could actually mix and match different products for different applications and different requirements. So again, building up a type of toolbox. So this also would mean that we need fewer products to be able to deal with the various applications and requirements of the metal finishing world. So 2K concept, basically what we have is a typical builder package. We call these our Uniclean B products, and an additive package, which we call our Uniclean A. So the additive package is mainly the surfactants and additives that are compatible. And again, the B package, the Uniclean B, would be a builder's package, so potassium hydroxide, sodium hydroxide, and whatever compatible additives there are. And by doing this, you should be able to reduce the amount of water you have in the liquid package and have high concentrations and good shelf lives. So taking all that into consideration, we've just given you a bit of an idea of how we went about modernizing some of our cleaner processes. Here is a new soap cleaner process that came out of that program. We call it the Uniclean A101. Again, that's a surfactant package, and the additive package, Uniclean B201. So we have two components for one process. And this is our ultra low temperature multi-metal soap cleaner. So we say ultra low temperature because instead of running at say 50 degrees centigrade or even 40, 45, this runs at 35 degrees centigrade. We have medium alkalinity, and this allows us to also use this on not just steel, but also copper and zinc alloys. And again, we have managed to remove things like phosphates, hard chelators, etc., all of the chemicals we mentioned before that were a substance of concern. And as you can see here, we have a wide temperature operating window. Even though the bath was designed to run at 35 degrees C, you can increase it if this is necessary for whatever application you have. So just to give you a bit of an idea, this is what the two components look like. The surfactant component looks quite dark and brown, and the builder component, the B201, is just a clear liquid. And again, the bath then looks like a dark brown soap cleaner bath. And as you can see here, we used it at quite low concentrations, so roughly 15 mils per liter of the A101 and 28 mils per liter of the B201. And again, low temperatures, typical immersion times of say 2 to 10 minutes, roughly 5. And again, it's good with nearly all substrates apart from aluminium. There is just a little bit too much sodium hydroxide in there for it to not attack aluminium. So it's good for all metals apart from things like aluminium. And on top of this, we also managed to make this process compatible with our long life technology, and also with our capable of being controlled by conductivity. So we're quite happy with this process. And this gives you a general overview of the process in a nutshell. Again, as we said before, it's basically everything free, which was important for us to make sure that this was at least as modern as possible. We have, of course, the low temperature operation at 35 degrees centigrade with all of the benefits that comes along with it. It's long life, so you get fewer makeups. We can also degrade oil over time to also increase the lifetime. And again, you can reduce process costs by having fewer makeups per year. And again, liquid products, ideal for you for handling. You can use conductivity control, so for automatic control. You can have dosing pumps, we mentioned that at the end, and good for different metals. And because we have two components, you can also adjust the bath according to your application or requirements. Just to show you some of the benchmarking results, we did some various testings with various cleaners. We took one of our current top sellers, best cleaner, soak cleaners, and compared this. We compared that at 50 mils per liter, so 5%, so slightly more concentrated than the operating makeup of the A101, B201, but we thought this was best for good comparison. And again, test everything under the same conditions. And we did various tests as we mentioned before. So here we talk about cleaning performance. Here's just some results from gravimetric testing. And here's just some examples from 4 different types of oils. One's a rust preventive. As you can see, relatively, both of them are cleaning this very, very efficiently. There's metal processing fluids. The new process was significantly better. Metal working fluid, again, the new process was significantly better, and again, thread cutting oil. So what we found is that by formulating a new cleaner, we could improve the ability on some of the more difficult to clean parts, oils, sorry. Again, you can see this in any visual results. So here you can see the benchmark process of record versus the new process, and as you can see here, significantly better results. The same can be seen for oil capacity. Again, we have just shown you this selection of same oils. Again, what you'll see is that we get the same or better oil capacity for the new process versus our process of record. And we saw that especially for naphthenic and these thicker, heavier distillates, this process was a lot better. So this also widens its usage and helps to increase the lifetime when those types of cleaners are used. And again, because we're using lower concentration for this process, then just because we're running at sort of a total of 43 mils per liter versus 50 mils per liter, we get the same or better results. Just by that alone, we can minimize shipping and storage of product by 14%. So again, we've managed to reduce storage and shipping costs by concentrating up the process and making it the same or more efficient than the process of record. So basically what we've shown you is that we've developed a new method for developing new cleaners. We've developed a new cleaner process based on our new toolbox and modern cleaners concept. And it's also capable to be used with things like our long life oil degradation. So we also wanted to introduce this to you. Basically, how this works is typically the more parts you put through a cleaner, the more contamination builds up in the parts, and a emulsifying cleaner only has a certain capacity. And after a while, the cleaning performance goes down and you have to dump the bath. If you could find a way to remove the oil that's been emulsified in the cleaner bath during operation, this would help to reduce would increase the effectivity or the effectiveness of the cleaning and would increase the lifetime of the cleaner. So if you think of a standard soak cleaner, you're putting in a lot of parts, you get then degradation of cleaning performance, which means this forces a new makeup. Again, you get degradation of cleanliness, and then you're forced to do a new cleaner. If you have a way of degrading some of the oil during the process, then actually you can maybe use the bath for longer, because the oil contamination is above the threshold, or sorry, below the threshold for having to replace the bath. And by doing this, you have a lot less work and time needed for new makeups, and of course the cost and the waste involved. So to do this, we have our long life technology, and this helps to degrade oil during operation, so while the bath is cleaning. And also we have equipment which we call our Isotect solution, and there we have a tub basically full of high surface volume parts, as you can see here. And by doing this improves the oil degradation, and also we can inject a little bit of air to help the process. So basically this is a way to increase the length the bath lifetime of a soap cleaner. On top of this, we mentioned earlier that conductivity control is a nice feature. We mentioned this because quite often people want to minimize the analytics that need to be done. They want to minimize people near a operating plating line, for example. Taking a sample out of a plating line can be a risky business, etc. So some people want to have very fixed, easy, automatic control. And one of the methods for controlling a soap cleaner is to use the alkalinity, the sodium hydroxide, for example, that's in the cleaner itself. Use this as a guideline, as this is a salt. This then reduces the conductivity of the bath itself. And by measuring this conductivity, you can then see if the amount of sodium hydroxide and of course the rest of the bath has been depleted to a certain level. This will then indicate a higher and higher and higher conductivity. And when this conductivity, lower and lower conductivity, so higher resistance. Once this conductivity goes below a certain baseline, you then can tell the system to dose a certain amount of chemistry to increase the conductivity again to the desired working level. So this is quite a useful feature, and we offer a system for this. Basically, the system is based on a conductivity sensor. We have dosing, of course, dosing pumps for the two components, the A101, the B201, for example. And you have a conductivity controller that measures the conductivity of the bath. And when this level of conductivity is triggered, then dosing starts for a certain amount of time. And then the dosing nozzles basically dose the correct amount of product into the bath to increase the conductivity back to the operating level. And by doing this, you can have more steady state cleaning than analyzing once per day or once per week and then adding several liters over the side in one go. So this is very useful for lifetime, for consistent process control. And in this case, as you can see here, this is a typical setup with the dosing pumps and also with various level sensors saying when the process has run out. And here's two different cleaner tanks. So you've got two sets of chemistry and two sets of dosing pumps being able to run two different cleaner tanks or cleaner baths. So again, a nice feature that our new processes can also use to make them more universally acceptable. So in general summary, hopefully today you've seen a little bit about soap cleaners, what's involved with a soap cleaner, what the main components are, what are the main features and the main characteristics of a cleaner, and what we need to do to modernize them. We've briefly shown you that there are new cleaners on the market that are also very, very attractive, especially at running at 35 degrees centigrade, like our ultra low temperature A101, B201. And hopefully you can see that it is possible to modernize even such how should we call it, a very old style process like soap cleaning for the metal finishing industry. It is possible to modernize it. You can improve it. You can make it more operator friendly, more environmentally friendly, and also safer to use and cheaper to use. And hopefully this will show you that a newer portfolio of modern cleaners is on its way and suitable for future applications in the coming decades. So thank you very much. And now, Katarina, maybe we have some questions.
Yes, Neil, thank you very much for the presentation. And we will now proceed with our Q&A session. I would like to remind everybody that we will cover as many questions as possible during the Q&A session, and all the rest, of course, will be answered by Neil after the webinar by email. So Neil, I would say let's start with the first question. What came in is, can you use the ultra low temperature process at higher temperatures if required for a specific application?
Yes, basically I did sort of mention right at the beginning of the introduction of the A101 B201, although it was designed to run at 35 degrees centigrade, and it's important when you're designing a low temperature cleaner that you know what operating temperature you want to work at to ensure that the components remain soluble and in solution at such low temperatures. But we also know that for certain applications, you need very high temperatures. Up to 80 degrees is common. And so we also managed to ensure that the formulation of our A101, B201 was also capable of running up to 80 degrees centigrade, even though its typical range would be somewhere near the 35.
Thank you very much. Somebody wants to know, how do you control or replenish the ultra low process bath?
Okay. Yes, we have two components. We have obviously the builder component, which is highly alkaline, and then we have our additive product, which is less alkaline, shall we say. Typical soap cleaners, the easiest way is to control them by titration, by measuring alkalinity, so an acid-based titration. This is the most common method and is also the same method we would recommend and employ for our Uniclean A101 B201. You analyze the alkalinity using hydrochloric acid, the usual phenolphthalein type acid-based titration. This would then give you a number, and then you just correct based on this. So we would use the same method. Unfortunately, analyzing individual components and trying to control them is not so easy, especially with surfactant-based products. So this is why we say, first of all, analyze the alkalinity. This tells you where the B is at, and then add the A component in ratio based on your makeup. So if you added it at 13 mils per liter versus 25 mils per liter, then you would add it in that sort of ratio.
Thank you very much. Let me check. Can normal high temperature soap cleaners be used at low temperatures?
I would say it's not advisable. Some can, some luckily can, but like I said right at the beginning regarding the higher temperatures, cleaners have lots of different components, lots of different additives. You have a lot of surfactants in there, and these can suffer if they're used at the wrong concentration and at the wrong temperature. So what we typically see is that if you have a high temperature soap cleaner that is used at lower temperatures, you sometimes see that the performance is a lot less or a lot worse than previously, and at worst you can get things like oil out and various other issues. So again, you can get bath instability, but the main issue is that using high, what should we say, soap cleaners that were designed to be used at high temperatures and using them at low temperatures, we see that the performance is just terrible. They need the temperature to work properly. So what you'll find is you have to increase concentrations, immersion times, or dump the bath more often because they're just not working as efficiently as they could do.
Thank you very much. As we are running a bit out of time, this will be the last question for today. Can ultrasonic support be used with the ultra low temperature cleaner?
Yes, actually, yes. This is one of the things we also tested to ensure that there was no incompatibility. So yes, the low temperature cleaner can also be used with ultrasonic support. And as we all know, ultrasonic can improve cleaning efficiency quite a lot. So yes.
Thank you very much, Neil, for your time and for your great presentation. And that was actually it for today. Thank you, everyone. We really appreciate you being here today with us. There will be a replay of this webinar available within the next few days, and we will send an email with the replay link out to you then. For all our on-demand webinars, please visit artotech.com/media/webinars. And also, we will keep you up to date via email about all our upcoming webinars. Also, we kindly ask you to take a few minutes after the webinar to answer a short survey because your feedback is very valuable for us. So for me, there's only one thing left to say for today. Thank you very much. Stay healthy and safe, and I hope to see you next time. Take care. Bye-bye.
Bye-bye.